All right, how's it going? Welcome back to another video for numbers and sets. In the last video, we introduced this new section here on countability, and it's kind of a short one, but it's still a fun section, I think, to end out the video series with. And in the section, we are primarily interested in the size or the cardinality of different sets. Right, so we started to introduce this terminology, and then we also introduced some additional terminology to describe the cardinality of sets, where we talked about both countable and uncountable sets. Right, where we said that a countable set was a set that is either finite or it is infinite, and there is a bijection from that infinite set and the set of natural numbers. Right, and we really use the natural numbers as a tool to help us determine whether or not a set was countably infinite. Because of course the natural numbers, that was the first example that we had of a countably infinite set. Right, so that's what we talked about in the last one, or in the last video, I should say. And right here was kind of just a summary of what we proved in the last video. And I want to just quickly recap this right here, because we're going to be referring to these properties throughout this video as we go through a bunch of examples. Maybe I'll stand over here. So there are three equivalent statements that we showed. And remember, I think we showed that 1 proves 3 and 3 proves 2 and 2 proves 1 or something like that. But the first statement is that a given set A is countable. So meaning finite, or there's a bijection with it in the natural numbers. Second equivalent statement is that there is an injection from A into the natural numbers. And the third equivalent statement is that either there is a surjection, just going the other way, from the natural numbers to that set A, or A itself is the empty set. Right, and we needed to add that little condition in at the end in order to properly apply the well-ordering principle. Okay. But all of this being said, this is what we talked about in the last video. In this video, we are going to be going through plenty of examples of different sized infinite sets. And these are all going to be sets that we've been working with throughout the video series. So I think this is going to be kind of a fun video to end the series off with. So I'm excited, and I hope you are as well. So first thing, we have been working so far with the natural numbers, right? At least in the last video, as a prototype for a countably infinite set. And that was kind of one of the first number systems that we looked at throughout this video series. It's been a really common one, right? The natural numbers. But we might also want to ask the question, well, what about some of these other number systems? Because some of the other common ones that we've been working with are, of course, the integers, the rationals, and what the entire last section was about, the real numbers, right? So what about the sizes of these sets? So first thing that we're going to be doing is I'll probably just erase what we have right here, and we're going to take a look at the size of the integers. How big are the integers? And of course, hopefully it makes sense, again, if we think of the integers as all of the whole numbers, being positive and negative and including 0, that there are infinitely many of them. And there are going to be infinitely many elements in each of these sets. But what we're really asking is is this a countably infinite set, or is it an uncountably infinite set? Right, so we're going to start to examine the sizes of each of these sets, starting with the integers. All right, so first question of the video series. Is the set of integers countable or uncountable? Now, what I'm going to do is, and we're going to see that we're going to do this relatively often, is we want to compare whatever set we have with the natural numbers. At least that is a common technique to do in order to determine if a set's countable or not. And if we determine that there is a bijection from this set to the natural numbers, then it is countable. And if we can show that there is not a bijection, no bijection exists from the integers to the natural numbers, then we would say that z is uncountable. So what I want to do is to write out a function over here, and I'm going to call this function f. And f is going to map from the integers to the naturals. And I'll specify what f is in a second, but I also want to just draw out a number line real quickly, where this first number line is going to be, let's see. First number line is going to be the domain of the integers. So maybe we'll put z over here. And then this second one, notice that the arrow is not going both ways. This is going to represent the natural numbers. This is going to be kind of the starting point where this is 1, 2, 3, 4, etc. Where here this is going to be 0, 1, 2, and then maybe -1, -2, something like that. Right? So we want to determine if we can come up with a function from this top number line, from this top number line down to the bottom one right here, and we're going to construct this function f as follows. So we're going to say that f is going to take in a integer, and it is going to spit out one of two possibilities. So the first possibility is that it's going to spit out twice the value of that integer under the condition that that integer is positive. And then under the condition where the integer is either 0 or negative, we're going to write 2 times -n plus 1. And this is 1, n is less than or equal to 0, like this. Okay. And this might seem a little bit arbitrary at first, like why are we constructing a function in this specific manner? But I think by writing out the two number lines, we're able to get a visual picture, and then we'll get a visual picture for what's going on, but then we'll actually be able to answer the question of whether or not the integers are countable or uncountable. So let's just see what this function does, first of all. So I have 5 input values right here on the top number line, -2, -1, 0, 1, and 2. And maybe we'll just start with the top case, this first case right here, where we're going to look at the integers greater than 0. So when n is 1, f of n is 2. So 1 is going to map to 2. When n is 2, f of 2 is 2 times 2, or 4. So 2 is going to map to 4. And you can imagine if we had, I'll just try to extend this a little bit. If we had 3, that's going to be 3 times 2, or just 6. And hopefully we start to see the pattern here, that all of the positive integers, by how this function is constructed, they are mapping to all of the even corresponding natural numbers. Okay. Now, let's move on to the bottom case right here. And we'll start with the negative numbers. So if we plug in -1 in for here, we're going to get negative, or minus -1, or just 1. 1 times 2 is 2, plus 1 is 3. So -1 is going to map to 3, like this. Then for -2, we're going to have 2 times minus -2, or 4. 4 plus 1 is 5. So then this is going to map to here. And that takes care of these two. And then finally for 0, 2 times 0 is 0, plus 1 is 1. So what we see is that it seems like the positive integers are mapping to all the even numbers. 0 maps to the first natural number, which is 1. And then all of these negative numbers, you can see -1 goes to 3, -2 goes to 5. We can imagine -3 is going to go to 7. All of these negative integers are mapping to the odd natural numbers. So it seems like there is a function that that appears to be bijective. But we actually want to show that this function is bijective and doing it in the proper way. And showing that f is bijective, that would determine that the integers are countable. But if you remember from what we just wrote on the previous slide, which was the summary of the last video, we said that this set right here would be considered countable if we could construct a function f that is injective. We can go from an or if this is injective, going from here to the natural numbers, therefore that set is countable. So all we need to do is to show that f is an injective function. So let's just remind ourselves what that means. In order for a function to be injective, we must have that if two elements from the codomain are equal to each other, so f of n1 equals f of n2, that implies that the two corresponding elements from the domain are equal to each other, n1 equals n2. So let's just see if this is true for both of the cases in this function f. So we'll start with the n is greater than 0 condition. And in that case, f, we're going to look at, this is going to be the form for f of n. So then the left-hand part of the conditional statement would say 2n1 equals 2n2. F of n1 equals f of n2. That's what this is. Then we can see the 2's cancel out. So if this is true, therefore n1 equals n2. So at least the top case satisfies the condition of being an injective function. Then let's just take the bottom case, n is less than or equal to 0. And same thing, we can just go through this process where we first set this equal to itself, where we have n1 and n2. So in other words, we have 2 of negative n1 plus 1 equals 2 of negative n2 plus 1. And then we can go through the algebra, of course, right? The 1's are going to cancel, then the 2's are going to cancel, and then the minus signs cancel, and that leaves us with n1 equals n2. Like this. And because that's true, that means that the bottom case is checked off as well. So what we've just shown is that f is an injective function from the integers to the natural numbers, and because of that, therefore the integers are a countably infinite set. And let's just take a minute to think about what that means too. That is telling us that if the natural numbers are countably infinite and the integers are countably infinite, then despite what this might look like, the integers are in fact the exact same size or have the same cardinality as the natural numbers. And we might be saying, why is that the case? Why? Because it seems like all the positive whole numbers are contained in the integers and all the positive whole numbers in the natural numbers. But then the integers have some additional numbers over here. And the reason our intuition breaks down a little bit is because we're starting to look at infinite sets. So things that we might think to be trivial, when looking at infinite sets, all of a sudden makes this not trivial. And we just showed mathematically that z has to be countable, or countably infinite. So if we have two sets that are countably infinite, we say that they have the same cardinality, same size. Okay, so kind of an interesting property, right? Naturals and integers are the same size. But let's keep going, right? There are some other examples that we can go through, and we want to go through a lot in this video. So I'm going to erase the board, and then we're going to go through our next example. All right, so on to the next set that we are interested in. So we showed that the naturals and the integers are countable, but what about the direct product? I should say the Cartesian product, n cross n, or in other words, n2. And again, this is all ordered pairs, or all elements of the form a comma b, where both a and b are natural numbers. If this was z2, then a and b would both be integers. If it was q2, they'd both be rationals. R2, they'd both be real numbers, and so on. Right? So we're interested in determining if this set is countable or uncountable. Okay, and we're just going to go through a similar process by coming up with a function and determining if that function satisfies the property of being countable or not. So let's define a function f, which goes from the Cartesian product n cross n into the natural numbers. And again, we would like to determine a function that ideally is injective, because that would immediately give us an answer that n2 is countable. So what we can do is say that, all right, f needs to take in two elements from the domain. So maybe I'll write a comma b as inputs, and it needs to spit out a single natural number in the codomain. So what we can do is we can write 2 to the a times 3 to the b. In other words, essentially creating a prime factorization for a given natural number. And you can imagine too, if we had n cross n, we'd have a, b, c as inputs, and then we'd have 5 to the c as the function that we construct. And now it's just up to us to determine whether or not this function is injective. So if this function is injective, then we can say, let's just write out the condition again. So we have f of a1, b1 equals f of a2, b2. If this is true, then we must have that the corresponding ordered pairs are equal, right? So a1, b1 equals a2, b2. So let's check this. F of a1, b1 is 2 to the a1, 3 to the b1. And f of a2, b2 is 2 to the a2, 3 to the b2, like this. Right. And this is where we utilize the fact that we picked prime numbers as our base. Because we know that well, first, each number has a unique prime factorization, but also you can imagine if we had a 4 here, then there would be different ways that we could take various powers of 2 and 4 for a given set of a and b's. So by ensuring that the bases are prime numbers, and that if we were to generalize this to n to the k, if we take k different Cartesian products, we would just have k different prime numbers. The reason why we do that is because that forces us to say that if these bases are the same, then the corresponding exponents need to be the same. So that is kind of the key to telling us that a1, b1 is equal to a2, b2, right? And again, let's just remind ourselves what that means. That tells us that we found a function f that is injective from n cross n into n. Therefore, the Cartesian product n cross n is a countably infinite set, which means that the set of all natural numbers with 2 inputs is the exact same size or same cardinality as the set of all natural numbers with 1 input. And you can see how this could generalize too, right? If we, like I was saying, if we had n to the k, we could use the same argument to show that n to the k is a countably infinite set. So the size of n is the same as the size of n cross n, which is the same as the size of n cross n cross n. And it keeps on going, which is wild to actually think about, but mathematically it's true. Okay. So again, an example that might not initially make sense, but we can show through the use of injective functions and the natural numbers that these statements have to be true. Okay. Now let's keep going with this though, because there's more that we can immediately say just from this example alone. So maybe really quickly, let me just write out that we know that n is countable. So n is countable, the naturals. We also showed that the integers are countable, so they have the same cardinality. And then we just showed that n cross n is countable. All right. Now what I want to do is I want to come up with another set that, in a sense, combines some of these pieces that we have so far. So what I'm going to do is I'm going to come up with this set, z cross n. We're allowed to take the Cartesian product between any two sets, really, as long as what that tells us is that elements from this set, if we have a, b in this set, that a needs to be an integer and b needs to be a natural number. But we're allowed to take the Cartesian product between any two sets. And let's now determine if this set is countable or uncountable. And we can say, all right, well, we know that z is countable, so it has the same size as n cross n, which has the same size as n. All right, so we can go from here to here, and then here to here. So therefore, the set z cross n is also countable. All right. Might be saying, okay, why are we caring so much about this specific set of z cross n? And the reason simply is because this was from a while back in the video series, but when we were constructing various different number systems, we were talking about how we could construct the natural numbers from Peano's axioms, and then from there we could construct the integers, and from there we could construct the rationals, and this is where I'm headed. But if you remember some of the specific details of that video, the rationals were simply the equivalence classes of this set of z cross n. All right? And what that means is that they have to have the same size as z cross n. So if z cross n is a countable set, this adds on to saying that the rationals q must also be countable, which tells us that the set of natural numbers is the same size as this, as this, as this, and as this. All these infinite sets, regardless of which one in our head we might think is bigger, they all have the same cardinality. Okay, and that's kind of a subtle argument too, saying that the rationals are simply the equivalence classes of z cross n, but it's a subtle but an important one that we can use. Okay, so hopefully this makes sense, but we're going to keep going because so far we've discussed the naturals, the integers, the rationals. What's left over though is still the real numbers. So, and there's a little bit of a different argument we're going to make for the real numbers. So I'm going to erase the board and then we'll go through that one. Okay, on to the final, I shouldn't say the final set, but out of the common number systems that we've been working with of the naturals, the integers, the rationals, and the reals, this is the last one, right? Up until this point, n, z, and q have all been countably infinite. So in every other set that we've looked at so far seems to also be countably infinite. So that probably makes us want to ask the question, well, is every infinite set just countably infinite? And as you might be able to imagine, we wouldn't include the phrase uncountable or use that as a term if there wasn't a set that was uncountably infinite in the first place. And it turns out that the set of real numbers is going to be the first set that we encounter that is uncountably infinite. So it's the first set that we can say, is it countable or uncountable? This first one we can circle and say it is uncountable. But let's actually show that. And the proof for doing that I think is really, really cool. It's called Cantor's diagonal argument. And essentially what he does is he does a proof by contradiction where we start by assuming the opposite. We're going to assume that R excuse me, we're going to assume that R is countable. and then arrive at a contradiction. Now, up until this point too, we have shown sort of rigorously that the definition of what it means to be countably infinite is if there is a bijection from a countably infinite set to the natural numbers. And then we just said an uncountably infinite set didn't have that property. But we haven't done a whole lot with developing our intuition for what a countably infinite set versus an uncountably infinite set looks like. And I want to just do that really quickly because we're going to refer to that in this proof right here. So let's say we're looking at the natural numbers, and if we were to write out all the natural numbers, we would start with 1 and 2, 3, 4, 5, and we could write out a comma-separated list of every natural number if we were able, in theory, to go on forever. You might be saying, like, yes, of course we can do that. But we can do that with each of these three sets, but notice that with the set of real numbers, we're going to run into a little bit of a problem if we try to do that. And here's the specific problem. Let's say that the first number that I'm going to look at is 0. And I'm going to say, okay. And then let's take the next positive number after that. And then I'd ask the question, well, what is the next positive number after 0? And we might say, well, maybe it's, because we're allowed to have decimals, right, with the real numbers. So maybe it's 0.1. But then we might say, well, wait a minute, there's also 0.01, and that's less than this one. So if we go to 0.1, then we've skipped out on the number 0.01. So maybe we should be writing 0.01 instead, 1/100th. But then we could apply the same logic. We say, okay, if the next positive number is 0.01, what about 0.001? Is that the next positive? And you can see how we could add as many zeros as we want. And the idea behind this is that between any two real numbers, we're always going to be able to find another real number that lies in between the two. So to say what is the smallest positive element after 0, the question, the answer is, well, you can't really describe one, because if you were to try to say there is this is the smallest positive element, you can always find one that is the halfway point between these two. You can always find a smaller one. So in terms of our intuition, we can think of a countably infinite set as a set which you could write out a comma-separated list and include all of its elements. Whereas with an uncountably infinite set of real numbers, that is just not possible. We are not able to write out a list that has that property without skipping over infinitely many different real numbers. Okay, so hopefully that makes sense, and we're going to use that in this argument right here. So if we assume that R is countably infinite, then we should be able to write out a list that goes on forever, of course, but a list that contains all of the real numbers. So we should be able to write out real number 1, real number 2, real number 3, real number 4. And this would go on infinitely. And if we were to write this out in the general case, real numbers are going to contain decimals, right? So we can write out all the stuff before the decimals. And maybe these are integers, they're just some positive or positive, negative, or 0. There's some whole numbers, what I'm trying to say. Then we have the decimal point. And then after the decimal point, we're going to have a bunch of these d values right here. And what these different d values correspond to, what they represent, are digits after the decimal place. So they're going to take on values from 0 all the way up through 9. And of course, you can imagine that if we're going to contain a very general real number, that each of these decimals should go on infinitely. Or we in the general case, we can write out these decimal points, or the digits after the decimal is going on infinitely. So I should put dots here, like this. Okay. So hopefully this makes sense as the setup. We could write out a bunch of real numbers this way. And now this is where the really clever part is, in my opinion. What Cantor does is he says, all right, suppose this is the list of all the real numbers. Well, let me write out yet another real number, r. And if r is a real number, and this is the list of all the real numbers, assuming it's countable, then this number r should be somewhere in this infinite list, right? But here's what we can do, and this is where the diagonal part comes in. You can imagine that if we were to draw out sort of a diagonal bubble, where this bubble would continue on infinitely, and if we were to just contain all of the digits, or if we were to look at all of the digits along this main diagonal, and I use main diagonal kind of like the main diagonal in a matrix if we're familiar with linear algebra. What we can do is we can construct a real number that has some integer before the decimal point and then some digits after the decimal. And these digits after the decimal are going to have a very specific property. And here's what the general property is. For any of these digits in the decimal, we're going to write that d sub n is going to be equal to 0 if d sub nn is not 0, and it's going to equal 1 if d sub nn is 0. Okay? Now what does that mean? Well, d sub n has one subscript. So this could be d sub 1, d sub 2, d sub 3, d sub 4. But notice that the value of d sub n is dependent on the value of d sub nn. And d sub nn would be like d sub 1, 1, d sub 2, 2, d sub 3, 3, d sub 4, 4, and so on. So the value, what we're trying to say is the value of these decimals right here are dependent on the values of these circled, or I should say, the value of these digits right here depend on the value of these circled digits right here. And they are specifically set up so that, maybe let's just set n to be 1, so we have a concrete example. If d sub 1, 1, meaning this digit right here, if it is not 0, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, then we're going to explicitly set this first digit to equal 0. And then just vice versa. You can imagine if this first digit is equal to 0, we're going to set this first digit to be anything but 0. So we're going to set it to the number 1. And we're going to do that for every single decimal, or every single digit after the decimal point. And what that does is that says that no matter where we try to fit this real number r into this supposed list, this real number r is guaranteed to differ from any of the real numbers in this list by at least one of the digits. And why? Because we set it up. We set up these digits after the decimal point so that there's guaranteed to be a mismatch in at least one of the spots. So basically, if one of these are going to be 0, when the corresponding element here is not 0. And this is going to be 1. One of these elements are going to be 1 when these elements are not 1, or specifically 0. Okay. So by guaranteeing that one of these decimals, or I keep saying decimals, that one of these digits after the decimal is different from every number in the list, what that tells us is that no matter how many real numbers we were to write in an infinite list, we are guaranteed that we can find another number that is not in that countably infinite list. But the contradiction comes about because we said this was the list that had all the real numbers. But if we found another one, that means that we must be at a contradiction. Therefore, the set of real numbers is uncountable. Really, really cool proof. And take some time to think about this too, because it might take a little while for it to click. but just a really, really cool argument showing that we have an uncountably infinite set. So hopefully that makes sense, at least the process for this. Now, I want to just quickly mention something too. Even though we're not going to prove it in this video series, there's something called the continuum hypothesis. And I recommend that you check this out on Wikipedia or just Google or whatever, which the continuum hypothesis essentially says that the set of natural numbers is countably infinite. So you can write out a comma-separated list of all the numbers. The real numbers is uncountably infinite. And what the continuum hypothesis says is that it is impossible to prove or disprove whether or not there is an infinite set that is larger than the natural numbers but smaller than the real numbers. Because we've just shown that the size of the real numbers is larger than the size of the natural numbers. But is there a infinite set that lies in between them? The answer is we don't know. And not just we don't know, but we can't know. It's really, it's kind of a mind-blowing thing to be able to prove a lack of knowledge to a question. But it's really a thing. And it's called the continuum hypothesis. Okay. So highly recommend just checking that out. Now, we have gone through our first example of an uncountably infinite set. I want to show another example of an uncountably infinite set. So I'm going to erase the board, and then we're going to go through that one next. All right, on to the next example of an uncountably infinite set. And here it says that P of n is uncountable. Now, let's just first remind ourselves what sort of this curly looking P is. This is the symbol that we used way back when talking about sets. This is the symbol for the power set, okay? And just to refresh our memory, the power set of a set, I'm going to say the word set a lot, but the power set of a set, this in itself is a set that is the set of all subsets of whatever the input is. Okay, so this corresponds to the set of all subsets of the natural numbers. And we want to show that the power set of a countably infinite set is uncountably infinite. How do we do that? Well, here's what we can do. We're going to set up a function. It turns out the proof is actually somewhat short, but it's still a really clever one, or at least the one that I want to show. We're going to set up a function that goes from the natural numbers into the power set of the natural numbers. And this can be an arbitrary function. And what we would like to do, if you remember, in showing that a set is countable, what we want to do is we want to show that there would exist a surjective function from the natural numbers into whatever set we're looking at. But now for showing that it is uncountable, what we would like to do is to show that there is no possible surjective function that exists that has this property. So how do we show that there's no surjective function from the naturals to the power set of the naturals? Well, what we can first do is we can first show that, or we can first say that f is going to be an arbitrary function. So that way, every statement that we are making is going to be true for any function that we're looking at. Okay. Now, what I want to do is I want to construct one of the elements of the power set of the natural numbers, and I'll call that element A. And A is going to have the property that it is the set of natural numbers, or it's going to be the set of natural numbers such that these natural numbers are not in the codomain. Okay, because natural numbers are or the domain, and then when f acts on a natural number, this is an element of the codomain. Okay? And by constructing a function this way, what we are inherently doing is we are picking out the natural numbers that are not in the image of whatever function we're looking at. And that right there is really important. I think I'll just say it again just to reiterate its importance. We are constructing a subset, so an element in here, of the natural numbers where these natural numbers are not elements of the image of f. And here's why that's important. In order for a function to be surjective, you need to have that the codomain, this set, is equal to the image. The image is the entire codomain. That is one of the properties of a surjective function. But what we are inherently doing is we are finding elements that are just not in the codomain. And since we can always do this, we can always find, or we can always guarantee that the codomain will not, or the entire image will not be the codomain. So by constructing a subset A of the power set of natural numbers in this manner right here, we are guaranteeing that f is not surjective. Okay, and really take your time to think about that, because it's a short argument, but it can be a little bit dense, because there are a lot of important words just in that statement by itself. But the reason that's important is to show that if there's no surjective function, then therefore it cannot be countable. Because if you remember at the very beginning, we said that A is countable as a sentence is equivalent to saying that there is a surjection from the natural numbers to whatever set we're looking at. So we replace A with the power set of the natural numbers, and then we can just take the contrapositive by saying if there's no surjective, then therefore it's not countable, or it is uncountable. Okay. So we now have two examples of an uncountably infinite set. We have both the set of all real numbers and now the power set of the natural numbers, or more generally, the power set of some countably infinite set. Okay. And maybe just to quickly mention too, the reason why we're specifying a countably infinite set is because if we have any finite set, the power set of a finite set is just going to be another finite set. It's going to be 2 raised to whatever the size of that finite set is. So that's why we are requiring why we are requiring a countably infinite set. Okay. Now, I want to just say one more thing, and notice that if we start with a countably infinite set, when we take the power set of the countably infinite set, we get an uncountably infinite set. So the general property of what's going on there is if we start with an infinite set and take its power set, then we get a larger set, because an uncountably infinite set is larger than a countably infinite set. And the question I want to pose to you is, does that property keep on going? Could we just take the power set of the power set of the natural numbers? And that's going to be the very last proof of this entire video series. And I wanted to save it for last because it's really kind of a mind-boggling statement. But I'm just going to erase what we have right here, and then we're going to go through that. All right, so on to the final claim in the video series. We have arrived at this point, and I'm excited to finally present this last, I guess, parting piece of math knowledge that I think is really, really interesting. It's a bit of a tongue twister, but we'll get through it. So basically, we already did this on the previous board, except all we're doing now is we're saying rather than letting the domain of our function f be the natural numbers, we're just going to let it be an arbitrary set A. And here we were showing that there's no, in the previous board I should say, we were showing that there's no surjective function from the naturals to the power set of the naturals. If we generalize that to some set A, the argument is the exact same. What we can do, we can just construct a set in this codomain, which is going to be the elements from the domain, such that whatever this function is, A is not an element of f of A, like this. Okay? And by doing this, you use the exact same logic to show that this is not surjective. But what is really important about this is that this statement is true for an arbitrary set. Okay? And that's important because if this is true for an arbitrary set, that effectively tells us that the cardinality or the size of the power set of A has to be larger than the size of A. Now let's start to put the pieces together. Let's specify what this set could possibly be. Let's say that we have natural numbers, and I might be butchering notation slightly, but you're going to get the point. That let's say we have we're going to look at the cardinality of the natural numbers, and we know that it is countably infinite. This has to be strictly less than the power set of the natural numbers, essentially by this theorem. And this is uncountably infinite. This is the same as the cardinality of the real numbers. But now, let's take the power set of the natural numbers. This is just a set, right? That's all it is. It's simply a set. And let's replace A in this general statement up here with the power set of the natural numbers. If we do that, this should be less than the power set of the natural numbers. And you can imagine we could keep on doing this. We could apply the power set to whatever this input is as many times as we want. So then this should be less than the power set of the power set of the power set of the natural numbers. And it could go on infinitely. So what's the conclusion of all this, right? So if we want to ask the question, how many different infinite size sets are there? Because up until this point, we've been working with two, right? We've been working with countably infinite, like the naturals, the integers, the rationals. And there are uncountably infinite, like the real numbers. But are those the only two sizes? And the answer is no. It turns out that there are infinitely many different sized infinite sets. And those infinitely many different sizes could be attained by just continually taking the power set of whatever infinite set you have. Unbelievably cool. And just mind-boggling to think that not only can you compare different infinities, but there are infinitely many different sized infinities. I don't know how to end the video series on a better note than that, right? Thanks so much for watching. A couple things just as sort of last final words. First of all, this is the first ever video series that I've made. So I'm doing this as a hobby, and I'm hoping that I can continue to keep making these videos. I have no plans on stopping. Right now I have 2 more video series that are getting planned out right now, that specifically group theory and linear algebra. And we're just gonna keep on making videos with that. So I'm really excited for that. And I hope that you guys continue to stick around beyond just numbers and sets. Also, there are problem sets that I am linking in the video description. And up now that we've gone through basically everything, or we have gone through everything, right? You in theory do have the material or have the knowledge to solve each of the problems on the problem sets. And I know this because I have solved each of the problems on each of the problem sets. And one of the things that I was contemplating when making this channel is I knew I wanted to make lecture style videos. I thought that was always just really fun, something I've always wanted to do. But I've also considered making videos where we have a separate video for each solution to each problem in each problem set. Almost said problem set, reminds me of power set, right? And right now I'm not quite sure that I'm able to post those videos without some sort of copyright issue, so I'm holding off on that in the meantime. But if that is something that you would like to see, you think that would be beneficial to learning the material, then let me know. I'm happy to try to talk to Cambridge University or whoever I would need to talk to in order to publish videos like that. But just know that for now, I am not posting videos like that for that specific reason. Just want to make sure that I'm not breaking any copyright laws. But yeah, thanks so much for watching. I really appreciate it. This is stuff that I just do on my free time. And the fact that these are getting any views at all, even though the view count is small, admittedly, is really cool to me. I appreciate you guys watching these videos, and I don't plan on stopping. So yeah, hopefully I'll see you guys in the upcoming video series.